We will talk about point set topology of the real numbers, and we are not going into much detail of this point set topology. We have to reach at Bolzano-Bosch task level, and for that, some of the requirements will be discussed, like neighborhoods, cluster points, limit points, and a brief introduction to and the closed and open sets. I will begin with the concept of neighborhood of a point in R. Uh, let me let us take a real number and delta be any positive real number, then the open interval, then let us call this open interval whose endpoints is c minus delta and the other endpoint is c plus delta. Then this open interval is called a delta neighborhood of point C. And this delta neighborhood of a point C is also given some other notation. It is denoted by other notations like you have n sub delta C or n C delta or B C delta. Note that what this interval is and where does this C lies. You have somewhere here C minus delta and you have here C plus delta, and C is the center point of this interval and delta is the distance of the left and right endpoints from this center. And because of this delta is sometimes also known as the radius of this delta neighborhood. This delta is the radius of this neighborhood and C is center of the neighborhood. They are this open interval. More generally, a subset U of R is said to be a neighborhood of some point C in R if there exists a real number, there exists a delta neighborhood, of C, and that delta neighborhood must be lying inside U. That means any set which contains a delta neighborhood of some point is a neighborhood of that point. This is as simple as one can say. Let's look at the let's look at this set. I will take this set U equals to R and I will see, and let C be an arbitrary real number. And note that whatever delta you choose, the open interval, which is also a delta neighborhood, the open interval whose endpoints are C minus delta, C plus delta, this is all subset of real numbers, hence it has to be in R. So this open interval is actually by definition a delta neighborhood of the point C, and it lies inside R. Hence, by definition of open neighborhood, it follows that R is a neighborhood of C. From this example, one thing I'm going to observe right as an observation. You see that R is a real set of real numbers, and that real number C that I took in R was an arbitrary, and we've been able to establish that this R is a neighborhood of this real number C, and it implies that this R is neighborhood of each of its points. So such sets, there are some other sets also. Not every set has this kind of property, and the sets which have this kind of property will be given a special name. They will be known as open set. But before that, let's observe some other things. Uh, Note that, as seen in the earlier part in the first half of the chapter, uh, any open interval, in particular any delta neighborhood, C plus delta, is a is an uncountable set. This is what we have done in our first half of this chapter. That every open interval is an uncountable set. Hence, it implies that since superset of uncountable set is uncountable, and you know that this or neighborhood of any point is a superset of some delta neighborhood, and that implies that neighborhood of any point, neighborhood of any point, any real number r, is always a countable, uncountable set, uncountable set. So this is one of the identification through which you can. This is one of the what you say the necessary condition of a mm, neighborhood of a point. That means if you have a set, for example, let us elaborate on this point further. For example, uh, note that the set rational number, set of natural, and set of integers are all countable sets. They are countable sets, and so they cannot be neighborhood of any point, because for set to be a neighborhood of some point, it has to be, first thing is that it has to be uncountable. Hence, these sets Q, N, and Z are not neighborhood, are not neighborhoods of any point. Another observation you might see, which will work, uh, which will also help you to identify whether a given set uh, is a neighborhood or not. Note that each note that this important property of real numbers is also known as denseness of real numbers, and it states that between any two real numbers, there are infinitely many, rationals. The rational means rational numbers and irrational, irrational. So what it implies? It implies that this gives us this gives us that any open interval or closed interval A B, that OAB, which is a open interval, and A less than B. So A and B are distinct real numbers. So you are going to have, and this open interval contains all the real numbers between A and B. Hence, we will have infinitely many real, rational, and irrational numbers between A and B. And that means this open interval contains both rational and irrational. And not only one or two rational irrational, it contains infinitely many rationals with infinitely many irrationals as well. So this observation also helps us to identify a certain extent whether a given set is a neighborhood of some point or not. For example, let us consider this set X. Okay, let us consider this example. Let us consider a set U be equal to mm, a real number such that mm, how I'm going to consider this. Let us apply this number at a certain point. I will just try it. No, okay. Let me take a simpler indeed. Let us take U to be a set of all those rational numbers such that R is greater than or equal to 0. So this is just to demonstrate, and note that this set contains only the rational numbers. And for this set to be a neighborhood, for a neighborhood there are irrational numbers also. So it doesn't contain any irrational number. Hence, this U cannot be a neighborhood of any any point in it, because a particular it cannot be neighborhood of any point. Okay, these are some of the techniques. And in classroom, I have discussed this about this set of rationals and set of integers and set of naturals not being neighborhoods, not by using this countability argument. But this is also important argument or other way to justify this statement. Okay, I will go to the definition of an open set, but before that, I'm going to do an important thing that let us take I to be an open interval AB, and then I'm going to establish that this I is a neighborhood of each of its point, each of its point is a neighborhood of each of its point. So how I'm going to prove it? Let us take let us take element C in this open interval AB, and what do you have? What do you have here? Um, Suppose you have this open interval with left endpoint A and right endpoint B. Suppose C is lying somewhere here, and let this distance, you have a certain distance this, and this distance can be computed to be C minus A, and this distance is nothing but this is B minus C. And I have to show that this set I is a neighborhood of this point C, and C is an arbitrary point of this open interval A, and that will establish that this open interval is a neighborhood to each of its points. But to establish this, I need to find a delta neighborhood of this C, which lies inside this open interval A, B. So how we have to find at least one delta neighborhood, and I'm just going to find a one delta, and I'm going to get this delta to be a number which is minimum of the distance of C from between C and A, and another number is B minus C. So we have this delta, and clearly since C lies inside the neighborhood A open interval AB, and C is neither equal to A nor equal to B, so C minus A and B minus C both are positive numbers, and this delta is positive number. Then you must say that this delta is a positive number. Now we will show that uh, with center C and delta being the radius, we are going to claim now this thing that this C minus delta and C plus delta lies inside this open interval AB. Okay. Now, so to show that this is a subset of this open interval AB, you have to show that each element of this delta neighborhood of C is inside this open interval Y, and for that you choose an element Y in this delta neighborhood of C, And what it implies? It implies that C minus delta is less than Y, and this is less than further C plus delta. Okay. Now let us look at this thing. What do we have? We have, let me rewrite this well, delta here. Delta is minimum of C minus A and B minus C. So what do we have? We have delta is less than or equal to B minus C. That means if I take C to the left, I will have C plus delta is less than or equal to B. And also, from the definition of delta, you see that since delta being the minimum of the two numbers, so it cannot be larger than, either it can be larger than C minus A as well. So delta has to be less than or equal to C minus A. So what it implies? It implies that you shift A to the left, you will have A less than or equal to C minus delta. And let us combine these inequalities with this inequality here in the box. What it says that A is less than or equal to C minus delta, and this is strictly less than Y, and Y is strictly less than C plus delta, and see that C plus delta is less than or equal to B. And dropping out this C minus delta and C plus delta, what you have, you are left with this inequality. A is strictly less than Y, and Y is strictly less than B. And what it implies? It implies that Y is an element of this open interval A, B, and this completes this inclusion of this delta neighborhood of C being inside this open interval AB, and hence this implies that hence because you've been able to find a delta neighborhood of C which is inside this, which is a subset of this open interval AB, and this proves that this interval AB is a neighborhood. I'm just abbreviating neighborhood to NVD of C, and this proves this claim, this neighborhood of this set C. Is it clear? Yeah. Which okay. Now I'm going to shift to another thing, which is again built from these neighborhoods. Neighborhoods are very important in this concept topology. They build everything in the topology. And the first thing that we have to talk about is the concept of open sets. Now, what is an open set? A subset G of R is said to be an open subset, an open set in R if for each point of G there is a neighborhood of there is a neighborhood U of X such that that neighborhood must be inside G. That means G must contain at least one neighborhood of this point X. If you have this situation, then such a set is known as a open set, as we saw already. But let me give an equivalent definition to this. And the equivalent definition to this open set is, then we will create lots of examples of open sets. And equivalent definition of the open sets is given by this following, that a non-empty, let me call a non-empty only, a non-empty subset G of R is an open set if and only if G is a neighborhood of each of its points. So we have to a set which is a neighborhood of each of its point is an open set. And now from this theorem, I will try to prove after discussing this example, which I can find by prove by using this theorem. And note that we just proved that this R is the neighborhood of each of its points. So from this theorem, it follows that R is an open set. Also, the another example that we just discussed here in this that this open interval is the neighborhood of each of its points, and from this theorem, it follows that any open interval AB for any real numbers AB in R, where A needs to be less than B, only then this interval is defined. This is an open set. So you have now uncountable number of examples of open sets. You keep changing the value of A, B, you get lots of countable, you get lots of open sets. So there is no deficiency of open sets. There are lots of open sets, but at the same time, you can see that this set Q, uh, since it is not a neighborhood of any of its points, so ये किसी भी point का neighborhood नहीं है, तो so it cannot be neighborhood of ऐसे अपने points का भी neighborhood नहीं हो सकता. Similarly, set of natural numbers, set of integers, they are not open sets. Indeed, you can see that open sets, indeed, any countable set is not कोई भी countable set is not an open set. Yeah, this is it. Why countable set? Because again, as argued in the previous slide, that by definition of this open set, an open set must contain a neighborhood of each of its points, and each neighborhood is a uncountable set, and so open set is an uncountable set. So countable set cannot be a open set, but countable in case of countable sets, there is an exception to this empty set phi. This empty set phi is an open set because I can apply because the definition we cannot the definition works by default on it because we are giving the definition that for each point, but this C has no point, so we have to consider it as an open set. So except in case of countable sets, except the phi, because phi is a finite, phi is considered a finite set, so it works. It is a for countable also. That's why I'm pointing out this exception here. So it's done now, and now let's go and work on this proof of this theorem, and in which we have to show that an open set, a set is open if and only if it is the neighborhood of each of its points. We first suppose that the set is open. Suppose that G is a non-empty set and it is open. G is open, and we have to show that it is the neighborhood of each of its points. Let X belongs to G, and I have to show that G is the neighborhood of X. But by definition of an open set, since G is an open set, by definition of open set, there exists a neighborhood U of X such that X is in U and U is a subset of G. So this is the definition of. Now there is an observation which I do for you to verify, very simple observation, that superset of a neighborhood, superset of a neighborhood of a point is also a neighborhood of that point. So in our case here, what we have, G is a superset of a neighborhood U of X, hence it follows from this exercise that G is a neighborhood of X. Hence it follows that G is a neighborhood of X. So X was an arbitrary point of G, and we established that G is a neighborhood of X, and it follows that G is a neighborhood of each of its points. So the direct part is done. In the case of converse, we assume that G is a neighborhood of each of its points, and we have to show that G is an open. And to show that G is an open, the definition of G is open set, we have to apply this and to make sure that it is open through the definition of open set. And the definition of open set is that each point must have a neighborhood which lies again inside G, And let us choose an element y in G, and then let u equal to G. I can keep. So by hypothesis, G is a neighborhood of y. So then it follows that u is a neighborhood of y, and I can write u to be a subset of G. So it satisfies the definition of an open set. You've been able to find a neighborhood. You just need a one neighborhood. It is not mentioned that the neighborhood needs to be a proper subset of G. It can be anything. It must be inside G. So U itself, which is a G, and G is a subset of itself. So it works as a neighborhood of Y. And in this way, for each point in G, there exists a neighborhood of Y such that this neighborhood is a subset of G. And this proves that G is an open set. G is an open set. Okay. Okay. Uh, uh, this is equivalent. So you have two definitions of open sets now. But another thing, uh, the complement of an open set is an interesting thing also, and that's why we define it to be something. And the complement, let F be a subset of R, then we say that F is a closed set, if its complement, which is you usually denote it by FC, and complement is nothing but it is R minus F, is an open set. That means complement of open set is a closed set, or a set is a closed whose complement is an open set. So the relation between closed and open set is a set which is closed, its complement is open, and a set which is open, its complement is closed. But make sure that it doesn't say that if a set which is not open is a closed. No, there are sets which are neither open nor they are closed. We will see those sets also. Indeed, in case of rational numbers, uh, you can verify it, and we might also verify after uh, going through the concept of these cluster points and limit points. This set of rational numbers is neither open nor closed set. So this makes the air clear that it is not that a set, if you take any set, it will be either open or closed. In case of finiteness or infiniteness, the set is always is either finite or infinite, but closed and complete this open sets doesn't do so thing. And there is another result which I'm going to record for your reference, and we will not go into the proof of this or detailing proof of this. And it states, and which you can call it as properties of open sets also. And what it says the following thing. I will call it as a theorem. It says the following thing, that phi and R are open sets. Open, but they are also closed as well as closed. So you have sets which are both open and closed, and indeed, let me say, these are the only subsets of R which are both open as well as closed. There is no other proper subset of R which has this kind of property, which is open as well as open. This is not true for any other proper subset of R. So they are special, that's why they are mentioned here. And why R is closed? The definition of a closed set is that its complement needs to be open. What is the complement of R in R? The complement of R in R is the empty set P, and we saw that empty set is a open set. And similarly, the complement of phi is R, hence R is an open set, and phi is a closed set. The second thing that second property of open set is that arbitrary arbitrary union arbitrary union of open sets is an open set. Arbitrary union of open sets is an open set. And the third thing is finite intersection. Intersection of open sets. Open sets is an open set. And since closed set is a complement of an open set, and then if you apply this complementation to 2 and 3, and then the De Morgan law works there, and then it reduces, in case of 2, for closed sets, the property goes like that: arbitrary, in case of complementation, union is intersection, arbitrary intersection of closed sets. Intersection of closed sets is a closed set. And if you apply this complement part, De Morgan law, to this 3, then you get that finite union of closed sets. Finite union of closed sets is a closed set. So you keep these properties of closed sets and open sets in mind, and then these properties having in mind, you can create lots of examples of open as well as closed sets. For example, let us use immediately this result to establish that any closed interval, finite closed interval, I will take A and B are finite numbers, is a closed set. Is a closed set. You can see it. See, what is this? You have this A. Let us take this B. So what is its complement? Let it be F. So what is the complement? Let G be the complement of F. Complement of F means the points of the real numbers which are not in closed interval AB. That means these are the real numbers. These are the real numbers to the left of A and to the right of B. And the set of real numbers to the left of A is all those points less than minus infinity and up to A. But A is not included since A is always already included in F. And your union, you have elements to the right of B are B, any element which is greater than B, and it is less than infinity. Now you see what you have. You have this complement of this of closed interval F as a union of two open intervals, and this has been already established that union. In case of infinite, I haven't done it for infinite. I just did for finite intervals, but it works for infinite intervals also. That this is open, and the property of open sets is that union of open sets is an open. Hence, this union is a open set. That means G is an open set. And what is G? G is a complement of F, and hence, by definition of closed set, it follows that F is a closed set. F is a closed set. So this establishes. Now you can have lots of examples of closed sets. Indeed, the final example that I'm talking about is that any. This is also an example. Any finite set. Any finite set is a closed set. So I'm just giving you the description. Suppose you have a finite set. Let A be a finite set. So if it is a finite set, you can write finite set to be A1, A2, AK. Since the set has to be equivalent to some first k natural numbers, and then you can write it in the form of sequence, and you can locate these k natural numbers. If we suppose we have kept these natural numbers, these real numbers in increasing order, and you have somewhere a1 here, you will have somewhere a2 here, a3 here. It is not necessary that they all are having equal distance from each other. Some of them might be very close to each other. A4, so on up to maybe ak somewhere. So then you see the complement of this a is nothing but it is minus infinity up to a1, then union open interval. You don't have anything between a1 and a2. Then you have to take the union of a2 and a3, and union up to, you have to take a union ak minus 1 up to ak, and beyond ak also you have this set ak infinity. And now this is a union of open intervals, and the open interval is an open set, hence it is a union. It's a finite union indeed, but in case of open sets, arbitrary union of open sets is open, hence is a union of open sets, is a union of open sets, hence it is open. And what is this? This is the complement of a finite set A, hence A is a closed set. So now you have lots of examples of open as well as closed sets. You have every finite set is a closed set. But in case of countable set, you cannot say with definite that every countably infinite set is a closed set, as the case of, as I discussed already, that the set of rational numbers, which is countable, countably infinite, but it is neither closed nor is open.